Have you ever stopped to think about how we actually invent the materials that power our modern world? I'm talking about the stuff inside our screens, our sensors, all that super fast tech. For decades, it's been this slow, kind of painful process of trial and error. But what if we could teach an AI to, well, dream up brand new materials on demand? Well, hold on, because a recent breakthrough is doing pretty much exactly that.
Okay, so our story kicks off with a really special kind of material. And no, it's not the glass in your windows. This is its high-tech cousin, and it's absolutely critical for some of our most advanced gadgets.
They're called chalcogenide glasses. So what's the big deal? The secret sauce is in their chemical recipe. Specifically, what's not in it. There's no oxygen. See, normal glass is built on oxygen, but these are built around elements like sulfur and selenium. And that one little difference, it changes absolutely everything. And that unique chemistry gives them some incredible superpowers. For instance, they're amazing at letting infrared light pass through, which is the magic behind night vision and thermal cameras. They've also got these high nonlinear refractive indices, which is just a fancy way of saying they can bend light in really cool, complex ways, making them perfect for advanced optics. They even have low phonon energy, which means less energy gets wasted as heat, so they're super efficient. But here's the most important part. You can actually tweak the recipe to fine-tune these abilities. But here's the catch. For something like 70 years, designing new types of these glasses has been, well, painfully slow. Imagine trying to bake the perfect cake, but you're in the dark, just randomly throwing ingredients in a bowl and hoping you stumble on something delicious. That's kind of what it's been like. The scientists behind this new study have a name for it: the Edisonian approach. Just relentless trial and error. And as they point out in their paper, this method just eats up a ton of time and money, and it really, really slows down the pace of innovation. And this chart just lays it out perfectly, right? You've got the old way on one side, slow, expensive, a total shot in the dark, and you could really only focus on one property at a time. The goal is to get to the other side, a fast, efficient, data-driven approach where AI can predict and optimize for multiple properties all at once. Now, to be fair, scientists have tried using AI for this before, but the early models had this huge blind spot. They might be able to predict a single property, like, say, how the material handles heat, but they couldn't tell you the whole story. And in the real world, you need materials that are great at a bunch of things at the same time. Those early AIs just couldn't crack that code. So what changed? What was the big breakthrough? Well, the genius here wasn't just building a bigger, stronger AI. It was about fundamentally changing how the AI sees the material's recipe to begin with. Yeah, so instead of just feeding the AI a boring list of ingredients and percentages, the researchers had this light bulb moment. They thought, what if the AI could see the recipe as a kind of graph, almost like a social network, where each chemical element is a person, and the connections between them show how they're related and how much they influence each other. So here's the new workflow. First, you start with the chemical recipe, like this germanium, arsenic, selenium glass here. Then you simplify things by just classifying each element's concentration as either low, medium, or high. And step 3, this is where the magic happens. That classification gets turned into a graph model. All of a sudden, the AI isn't just looking at a list of numbers, it's seeing a structure, a network. And from that network, it can predict a whole bunch of properties all at once. Okay, this all sounds really cool in theory, right? But the big question is, does it actually work in the real world? Well, the researchers put their new model to the test, pitting it head-to-head against a bunch of other leading AI methods. And wow, the results are pretty darn impressive. When they tested it on the full dataset, their new model hit an accuracy score of almost 85%. I mean, just look at the comparison. It pretty handily beat the next best AIs and just left the older methods like DeepWalk completely in the dust. But honestly, this is the number that really blew me away. Get this, even when it was trained on just 10% of the data, the model still hit an accuracy of over 78%. That's better than some of its rivals that were using the entire dataset. It's not just powerful, it's incredibly efficient. And it wasn't just about the main accuracy score either. Looking at all the key metrics, like recall, which is basically how well it finds all the right answers, and the F1 score, which balances everything out, the new model came out on top consistently. This shows it's not a one-trick pony. This thing is seriously robust. So let's just zoom out for a second. We have a new AI that is faster, way more accurate, and a lot more efficient at figuring out the properties of these really complex materials. So what? What does this actually mean for us? Well, the bottom line is this. We can now potentially slash the time it takes to discover and design new materials from years down to, well, a fraction of that. This isn't just some lab experiment. It's a tool that could seriously speed up the development of everything from better medical devices to faster internet. Now, of course, the researchers are really upfront about the current limitations. The study was based on a dataset of about 556 glasses and focused on just 5 key elements. So the next steps are pretty clear. Get more data and teach the model to handle even more complicated chemical recipes. This is really just the beginning. And that leaves us with a really fascinating thought to end on. This breakthrough wasn't just about glass. It was about a new way to teach an AI to understand the deep, complex relationships inside a system. So if this kind of network thinking can revolutionize materials science, what other huge problems, everything from discovering new medicines to modeling climate change, could we solve by teaching AI to see the network instead of just the list?